Hey there, calculators. Welcome back. This is section 5.1, but it's actually the second section that we're talking about in this chapter. Hopefully you've already seen the video that I did for 5.2. And the reason we talk about 5.2 is to give this section just a little bit more context. But before we get there, I have three problems for you here to do. If we were in class traditionally, this would be like an opener, where you would walk in and you'd knock out these three problems. Because this part is a review. It is find the derivative of each of these three problems. And so we would say, oh, okay, all right, here we go. F prime of x is equal to, we just applied the power rule here. These are polynomials. 5x to the third, the derivative there is 15x squared, and the derivative of the constant of 7 goes away. I should say the derivative is 0, and so it appears to go away. Same thing, actually, here. G prime of x, 15x squared, and, the minus 4 constant is, the derivative of that is 0. And then when we look over here at capital H prime of x, 15x squared, and where the pi might throw you is you might, hopefully you don't, but you might have like a kind of a gut feeling to treat that as a variable, but it's not. That is a constant. It is just a constant we represent with a symbol. So we find out that all of these answers, all of these derivatives are actually the same, even though their functions are different. And that's going to come back into play in a little bit. But we are going to talk about the process of anti-differentiation. When we were doing the video for 5.2, we spent a large majority of our time focused on a function that we could not easily break into rectangles and triangles and circles or trapezoids or whatever. We were dealing with a function that was a relatively increasing function, but had lots of curves and lumps and bumps. And we learned a geometric trick of breaking that into rectangles smaller and smaller and smaller. Now that we've seen that in action, I'm going to be teaching you how to calculate that algebraically without having to do all the geometrical breakdown. So for instance, what we are going to be doing is taking the antiderivative or the integral. That is the area under the curve, but that also gives us a function whose derivative is the solution. And I know that sounds really convoluted and really messy, but I assure you it's not too bad. And this will lead into, this skill is foundational for the rest of the course. And honestly, if you're taking mathematics courses after calculus, is foundational to some of those courses also, because calculus is kind of the backbone of all of that. And you can see the notes here. I'm not going to read them to you per se, but I am going to highlight a few things that are important to look at. So the goal of differentiation is to find the derivative of a function. We are focusing on the reverse process. Is we are given a problem, let's say function f, we are looking for capital F. We usually use the capital letter to note an antiderivative, whose derivative is the original problem. So when we do problems down below, a little bit later in this video, I'm going to give you a function, and you are trying to find, your answer is the function whose derivative is the problem that I originally gave you. And we'll do a bunch together just so you kind of get the feel for that. It's really weird to explain in words. But there are also a couple of rules that make that process easier. So you're not just thinking and just racking your brain for, what function would do this for me? But we're going to teach you some shortcuts and some rules down below. So you can see we've talked about the integral sign here. If we attach that integral sign to a function, I'm looking for the antiderivative. I am looking for the function whose derivative is the problem that I was given. And then this expression, which you might notice from our last video, represents not only the area under that curve, but it represents the family of all the antiderivatives of f, and we're going to see what that looks like. Here is the deal, and here is what I want to focus on before we start doing some problems. We have two major rules. I'm actually going to take a look at this constant rule, constant multiple rule for integration first. Basically what this says to us is if I have a constant multiplied out in the front, let's say my function was x squared, but I was looking at 2x squared, I can actually, just to make my life easier, pull that constant out in front and then take the integral of the x squared by itself. And what that does is allows us to take the integral, and we would probably then use the power rule for integration. And you're going to see this in action, so I'm not going to talk too much. But what is important to note is this concept of this capital C. Whenever you take an antiderivative and you aren't plugging in numbers afterwards, which is something we'll do later in the chapter, we need to represent all of the functions that could have that derivative. As you see here, up in our opener of number 1, number 2, and number 3, there are multiple functions that have the same derivative of 15x squared. In fact, there are infinitely many functions because we could just plus or minus any sort of constant on the end and it would still have that same derivative. So for now, you just need to know that after I find any antiderivative, I'm going to literally write plus c to represent all the different vertical shifts of that function that would end up having the same derivative. And we're going to do that. So here we go. We have what might look like some complicated antiderivatives here, but we're going to make them as simple as possible. The first thing we're going to want to do, and we're going to focus on number 4 here, is to kind of rewrite this in a way that makes sense for us. So I'm going to first deal with this square root, because we don't have a square root rule for integration. However, and you've been doing this with derivatives, it is totally appropriate to write 3x to the 5th plus 2 minus 5x to the 1/2 dx. And that's a good start. We can further make this easier for ourselves by doing the following. Look at this. This red line here is the same as this purple line. But using the constant multiple rule and also using a rule that lets us separate these functions, I can break this down into actually 3 separate antiderivatives. And that's what I am going to do. So when I take the antiderivatives in this next step, I'm going to use this power rule, which says x to the something times the integral of x to the something dx is equal to x to one higher exponent over that old exponent plus 1. So for instance, this antiderivative here of x to the 5th is going to be equal to 3 times x to the 6th over 5 plus 1, which is 6, plus 2 times the integral of dx. This one is easy. When we ever take the integral of a constant, we are then just going to end up with that constant with x tacked onto it, or whatever our variable happens to be, minus 5. This one's a little more involved because we're using a rational or a fractional exponent. X to the 1/2 plus 1 is 3/2 over 3/2. And then don't forget, you will do this at least once, hopefully it's only once, to add the plus c on the end to represent whatever constant we have here. So now we're just going to do a little bit of algebraic simplification. 1/2 x to the 6th plus 2x minus, when we simplify all of that, it comes out to 10/3 x to the 3/2 plus c. And there is our antiderivative. And remember, what this means is that this function here, if we take the derivative of it, we will get back to the function we were given. That's one way to check your answer. Or you could use Desmos or a calculator to do that the same way. Okay, number 5 looks a little more involved, and you might be saying to yourself, oh man, is there a product rule for integration? Sadly, there's not, at least not yet. So what I'm going to ask you to do might seem a little counterintuitive, but I'm going to ask you to multiply these two factors out. So we are going to say that this is equal to, and we're going to distribute x squared times 2x is 2x to the 3rd minus 5x squared plus 2x minus 5, and notation-wise, that dx is very important. And then we have just one nice polynomial out there, and we are going to use our constant multiple rule and separate these integrals. So this is equal to 2 times the integral of x to the third dx minus 5 times the integral of x squared dx plus 2 times the integral of x dx minus 5 times the integral of dx. And so we're going to just kind of rip through this with our algebra. 2, using the constant multiple rule, x to the third, its integral, or its antiderivative, is x to the fourth over 4 minus 5. The antiderivative of x squared is x to the third over 3 plus 2 x squared over 2 minus 5x plus c. Don't be that kid that forgets plus c. And then your final step here is just to tidy up and simplify and multiply through these constants. So I get 1/2 x to the fourth minus 5/3 x to the third. The 2 and the x squared over 2 cancel, so just x squared. That's awesome. That's fun when that happens. Minus 5x plus c. And again, I've said it before, I'll say it again, and this is how conceptually it helps my students in the past the most, is if I were to take the derivative of my answer, I would get back to my original function, or in this case, since I had to do a little manipulation at the beginning, I would get back to this function here. Polynomials are relatively straightforward. Lots of power rule use. Just like when we were taking derivatives, we had a power rule for derivatives. It gets a little more complicated when we talk about some trig problems, and we're going to do some right here. We're actually going to do number 6 and number 8 together, and then we'll save number 7 for the end. There are more problems here, but we are not going to do those in this video. We will have those available as maybe openers for your class later in the unit. So we're going to focus on 6, 7, and 8 and call it a day. If you want to then practice 9 through 14, I highly encourage you to use the skills that I've shown you to try those problems out. Now, with trig, there's not a simple, oh, if you see this, then you automatically do this. It's more of a thinking game. You need to think, oh my gosh, was there a derivative of a trig function that gave me secant squared of x? And actually, there was. So by inspection, just by looking at this, if you remember what that is, you can be like, oh yeah, I remember that when I took the tangent, the derivative of tangent, I got secant squared. So it is very simple for us to immediately jump here and say, okay, well, if I go backwards, since secant squared is the derivative of tangent, the antiderivative of secant squared is tangent. And then we always tack on the plus c, because that could be secant squared of x plus 5, or sorry, tangent of x plus 5, or tangent of x minus pi. We don't know what that constant is. Similarly, for number 8, there is a derivative out there where I get the secant of x times the tangent of x, and that was secant of x plus c. If I took the derivative of this function, doesn't matter what the constant is, I would always come back here. And so some of those we do just by inspection. There's not really any work to show here. And when they're straightforward like that, that's awesome. Now the difference with number 7 is that we've got some chain rule action going on. We need to first think, okay, what function, when we take its derivative, gives us sine? And I'm going to show you the way that I kind of work these problems, even as someone who's been doing calculus for a number of years now. I kind of draw an arrow down saying, okay, the derivative of what function gives me the sine of something? And I know that the derivative of the negative cosine of whatever is in that parentheses gives me positive sign. And that's a start, but that's not all of it. So here's what I do down below. I say, okay, I take the derivative now of this. So what I do is I say, okay, the derivative of negative cosine. I know that's positive sine of 3x. But I also know that if I was given this problem, I would be doing a times 3 on it to account for the chain rule. So my answer here is 3 sine of 3x. And now that answer does not give me my original function, and that's a problem. But what I can do is I notice that my difference is only a constant. So how do I counteract a constant of 3 out in front? Well, I would put a negative 1/3 instead of a negative 1. And that counteracts right there. So the way I can check my answer, I would say my answer here is negative 1/3 cosine of 3x. And the way I check that is taking the derivative again. The derivative of negative 1/3 cosine of 3x is positive 1/3 sine of 3x times 3. The 3 and the 1/3 cancel out, and I'm left with sine of 3x as my derivative, which is my original problem. So therefore, this function here, and I almost did it, don't forget plus c, this function here is my antiderivative. Awesome. These take practice. These take time, especially with the trig derivatives where there's not a simple cut and dried rule like the power rule. Take your time in practicing. Take your time at looking at these problems down below. There's not a ton of trig in this page remaining, but this page will give you a good practice of the power rule. Ms. Drosick, Ms. Gogarty, and I will be working with you on the trig to get those skills down, but we feel that this video is going to give you a good start as you kind of jump into your studies for Chapter 5. Thank you again for being here, my friends. I appreciate you watching this video through to the end. I appreciate your time. And if you have any questions, make sure to email me or your teacher, and we will do our best to help you through it. Have a great one, everybody. Bye-bye.